2021, which surely can't be worse than 2020.
Don't jinx.
Hope you all had a good break. And so welcome back. We start up the astronomy seminar series again this term with Eric Bell. I've known Eric for quite a long time. I think we just missed each other in Durham. He graduated as a PhD student just as I was arriving as a postdoc. He then went on to spend time at Arizona and Heidelberg before getting his faculty position at Michigan, where he is now as a full professor. And he's made numerous seminal contributions to the study of galaxy evolution and the connection between stellar light and dark matter, the dark matter structure, dark matter halo structure that underpins that. Certainly one of the pillars of the field that most of us those of us have worked in for quite a while. So without further ado, I will just let Eric take it away. He said that he's happy for you to interrupt with questions. You can raise your hand and I can try to recognize you, but also feel free to just interject. That might be the easiest way to do it, and just ask questions as they come up. But there will also be 10 minutes at the end for further questions. So with that, welcome, Eric.
Thank you. Thank you for the invitation, and thank you for the kind introduction. I wanted to tell you about some work that my collaborators and I have been doing over the last, it's probably a decade, trying to understand the impacts that galaxy mergers have on both the host galaxies themselves, but also their satellites. My main collaborators in this are shown down here. Adam Smircina recently graduated and is now a postdoc at the University of Washington. Richard D'Souza is at the Vatican Observatory as a staff scientist. Antonella Montechesi is at the University of La Serena as a professor. And Ben Harmson is still working with me at the University of Michigan. He's a part-time astronomer and part-time rock star. He is a guitarist of a band. All right, so just to give us some kind of context, we're all pretty familiar with the idea that dark matter is the central driver of galaxy formation and evolution. We have the relatively early formation of dense nuggets of dark matter we call dark matter halos, and they grow through aggregation of each other by merging into larger and larger dark matter halos as the universe progresses. And this is really the part that makes galaxy formation hierarchical. Right? So this is one of the main things that we're trying to understand the impact of when we look at how galaxies form and evolve. Unfortunately, to us, all of this looks like that. Right? Because dark matter is dark. And so we have to try and figure out how to observe dark matter. I see a blue line. Maybe there'll be a dark matter trek. That might be how we observe dark matter. But for most of us, we're stuck with light, right? So the light from stars and the light from the gas, the gas condenses into the central parts of these dark matter halos and subhalos. So we have, here schematically just shown roughly to scale a galaxy in the middle of the largest dark matter halo, and then the largest dark matter subhalos containing satellite galaxies. And these galaxies, therefore, they reflect what's happening in this hierarchical growth, but in this very complicated and indirect way. And so it's been very challenging to connect the galaxies that we see to the hierarchical growth that we think is happening. Stellar halos offer a potentially quite powerful way of trying to understand this hierarchical growth. So it's using the stars that are in these subhalos, the satellites, and as they fall into the main galaxy and get tidally disrupted, they leave a structured halo of stars, which we can then observe and try and understand the properties of that do reflect the aggregated hierarchical growth history. Let's see what the chat is. No problem. No, the blue line was clearly a dark matter detection. It's no problem. And so this is, in principle, it could be a very powerful approach to try and understand hierarchical growth through understanding the stellar halos of galaxies. And so we've been using this approach as a community in the Milky Way for a while. And so we've been studying the stellar halo of the Milky Way, both in terms of its structure, but also in terms of its kinematic structure and chemical structure. And decades of studies have shown that the Milky Way has a relatively low mass, so 10 to the 9-ish solar masses or a little less, relatively metal poor, so 10th solar or a little bit less metal rich, stellar halo, with streams from both disrupting galaxies. And so here's, for example, the stream from the Sagittarius dwarf. There's the stream in the south. And here's a stream from it's called the Orphan stream. We actually don't know what it's from, except that it's a galaxy because it's relatively wide. But we also see some streams from globular clusters. This is the GD1 stream or the PAL5 stream from globular clusters. And so this kind of effort has given us really interesting insight that we'll be leveraging later on in terms of the hierarchical growth of the Milky Way. And so you'd like to be able to understand and generalize this to other galaxies. And so, here we encounter a kind of technical, I guess, a rather pedantic challenge that stellar halos and satellite galaxies are just really diffuse, right? They're very low surface brightness. And so they've just been super hard to detect around other galaxies. So this is an example of a Milky Way-like galaxy, NGC 5907, looked at edge on. And at normal sensitivity, it just looks like a normal run-of-the-mill galaxy. If you look at it with much longer exposures and trying to be as careful as possible about subtracting off the contribution of sky background, then some stellar streams are revealed around this galaxy that are somewhat reminiscent of the Sagittarius stream around the Milky Way. And so this offers kind of a template for how one might start to attack this issue. And this type of stellar stream is something that we can now study using long exposures on relatively small telescope coupled with careful data analysis, or just specially designed telescopes that are designed to have low scattered light. And so these have brought the streams into focus, right? Unfortunately, part of this is that you actually kind of subtract off the light from the more diffuse part of the stellar halo. So if you look at, if you want to understand the overall, the aggregate stellar halo, this trash can that contains the tidal debris from all galaxies, that's something that's still very, very difficult to observe. Yes, fair point. So Dustin points out that, let me point out this particular image here, that in particular, one of these streams has been contested. That does not change the fact that, that it has stellar streams. And it actually points out that, hey, this technique, even though it's very powerful, is still somewhat limited, right? So you'd really like to be able to measure this with as much fidelity as possible. So this is a good
absolutely, that was pedantic, sorry.
Sorry?
That was pedantic, sorry.
Oh, no, it's actually fun. And it's an important thing to realize that this kind of data is not bulletproof, right? That we see these images and we're like, yeah, I wonder how much to believe it, right? It's a hard business. And so I appreciate you pointing that out. And it's worse that you'd really like to understand the overall contribution of the stellar halo, which is much less structured. And so it's more difficult to observe. And so our team over the last years has been adopting an approach which is observationally much more expensive. It's really quite repugnant how much observing time it costs. And that's by trying to resolve individual stars in the diffuse outskirts of nearby galaxies using Hubble Space Telescope or Subaru to reveal the stellar halos and the faint satellites, right? So the basic roadmap we're kind of illustrating on this slide here. So here we have the Eris hydrodynamical model. And so this was meant to be a Milky Way-like model of a Milky Way-like galaxy with the stars that are in the kind of disk that were formed in the main potential. And then this thing they've labeled ex situ is the tidal debris from all the satellite galaxies that have fallen in as part of the hierarchical assembly, and is expected to make a diffuse envelope of stars, which dominates at large radius. And so the idea here is that you take a telescope and you plop a bunch of pointings pretty far out from the galaxy where there aren't many stars that formed in the middle of that potential well. And then you hope to be able to measure the contributions of these stars that formed in dwarf galaxies and then were tidally disrupted, which in turn would give you insight into the hierarchical growth of the galaxy. All right, so that's the basic idea. And so we've been doing this with HST for the GHOST survey for an embarrassing amount of time for the number of papers that we've produced, because it's hard work actually to assemble this type of data set. And you can see that the HST field of view is really quite small compared to the scale of nearby stellar halos. One way around this is by using larger ground-based facilities. So Subaru telescope has an enormous field of view with its Hyper Supreme Cam and can reach comparable stellar depths. The problem there is star-galaxy separation. And so we'll be chatting about this a wee bit, but I'm also happy to discuss this. And the advantage of this type of approach is you can cover much larger areas and get more of a global view of the stellar halos of galaxies, but with somewhat less sensitivity than you would have from space. And ideally, you use them both in concert. There's a chat message. So let's see what it said. How far out are these in effective radii? Well, so we're along the minor axis, and so the question is, how far out does this type of observation go in effective radii? And so we're typically pushing out to 50 to 100 kiloparsecs. And so in terms of a half-light radius of a galaxy, that would be something like 20-ish, give or take. And how far away these galaxies? So we'll talk about that in a wee bit, but the things we focus on are typically 3 to about 11 megaparsecs away. So they're local volume, right? As defined by, so Karachentsev has this lovely definition of local volume, which is if he can get the tip of the red giant branch in a single orbit in Hubble Space Telescope, it's local volume, right? And so that's the empirical approach that's actually, that they've used to build up this really very powerful catalog of local volume galaxies. And so for our purposes, we're really focusing on the nearby kind of 10 or 11 megaparsecs, which is, part way out to the Virgo cluster and Ursa Major cluster, for reference. All right, so let's give an illustration of what this kind of data looks like. Okay, so here we start with a familiar thing to Northern Hemisphere astronomers, the Big Dipper, and we're zooming in on smaller and smaller scales to a nearby galaxy, NGC 4244. This is about 3 megaparsecs away. And if you reach Subaru resolution, or eventually Hubble Space Telescope resolution, you start to resolve the galaxy into individual stars. And so what we're doing here is we're taking what you would normally do using diffuse light, using all the light from these stars together, and you're saying, that's too hard to keep track of, especially when it's low surface brightness. And I'm just going to find individual point sources, and I'm going to count them. And that's going to be a rather easier job. It's easier to do, but it's also observationally much, much more expensive. And so this, of course, is what beautiful data looks like. Our typical data set looks much more like this. And so you can see, that field does not have a lot in it. This is, you see here, there's actually a chip gap with some cosmic rays that we need to appropriately think about. There's a bunch of background galaxies. That's probably the main thing you see first. You do see a globular cluster here, and then what looks like a potentially partly resolved background galaxy. And so if you want to focus on objects that have the colors and brightnesses that are consistent with being red giant branch stars at the distance of this galaxy, this is a field in the outermost parts of M81, then this is, and then if you handily circle them in red, then these are the stars that you would then study. And you realize, oh yeah, that is a globular cluster. It's a bunch of red giant branch stars at a given distance. But then you also see that these red giants are spread all over the field. And so the idea here is that you use the red giants as the visible probes of all the other stars that are expected to be in that field. So with a typical kind of IMF and the expected star formation history and the distance of the system, you'd expect about 100,000 stars that are too faint to see with this telescope or any foreseeable telescope per circled star, right? And so there's going to be an extrapolation here, but it's using essentially the observed ratio of red giant branch stars in globular clusters or in dwarf galaxies or in stellar population models to all the rest of the stellar population to then infer the properties of the overall stellar halo. Are there any questions about this approach before I kind of show some of the fruits of the approach?
Just you do some kind of statistical background subtraction on a blank field or something, or some of these possible detections not real associated clusters?
Yeah, so we do some type of background subtraction. And so what in practice we do is go to fields that are very far away. So either the outermost fields or sometimes fields that are, many, many degrees away, but close enough in the sky that the background and foreground. A lot of these are also foreground stars, amusingly. So they're very, very faint halo stars, lower main sequence stars in the Milky Way stellar halo. And so we do need to be cognizant of that. One of the things that we've learned from our Subaru investigations is that we over subtracted in some of the ghosts. Stuff that that there's less contamination. So to zero order, almost everything you see here is a red giant branch star at this distance. And there are very few. So of order, literally 1 or 2 in this image of these is a foreground or background object. So it turns out to be a technique that's even better than we'd imagined. Does that help, Michael?
Yes, it surprises me slightly, but
yeah, it surprised the heck out of us too, right? That's, I think, why we over subtracted.
so you mean that if you looked elsewhere with a field of this size, you would basically see none of these red circles. This really is a...
And so here, what you see plenty of objects, right? So you look at cosmological fields and they all look like this with some, objects of various sizes, etc. The thing here is that very few of them have properties consistent with being point sources, and then also have brightnesses and colors that are consistent with being red giant branch star. Right, so most of the faint stars are actually somewhat bluer in the faint foreground stars in the Milky Way are rather bluer than the stars that we're studying here.
I guess sorry to belabor, but I guess part of the reason why it surprises me is that when I look at the distribution of these stars, and maybe this is the point, I mean, they don't look at all correlated with your target halo. They look uniform. If anything, they're correlated with other objects in the field.
Yeah, here, let's do, well, so first of all, that's a globular cluster. This turns out to be something at 12 megaparsecs from us, which was an accidental discovery. One of the reasons why it's okay that they seem quite smooth is shown here, is that one of these fields has a scale that's something like this. And so we actually don't expect a tremendous degree of structure from field to field, just because the fields are so small compared to the overall structure size. And then there's this great question of like, hey, wouldn't it be really cool to measure like a 2-point correlation function or something? And that would be cool, but we've not been able to do it with space-based data because we've had so little sensitivity to structure on kind of meaningful scales. And I think that in the future, that'll be something that's actually pretty interesting to do from the ground if we can handle star-galaxy separation enough. Potentially Roman Space Telescope will also be powerful for this. Does that work?
Yep, good.
Awesome, okay. I got my thumbs up. I managed to cut my thumb the other day, so I've got my Band-Aid up. All right, so let's generate a wee bit of intuition as to what this looks like. So we're relatively used to the idea of the Andromeda galaxy, the kind of nearest Milky Way mass galaxy to us. It's about 770 kiloparsecs away, give or take. let's go to a relevant scale for this kind of study, and then show the PANDAS map taken with a Canada-France-Hawaii telescope over, gosh, lots and lots of nights, right? It's a very observationally expensive effort, this and similar efforts, because you need to resolve individual stars. But one was able to map the entire stellar halo and the satellite population of the Andromeda galaxy out to about 150 kiloparsecs radius. Right? So that's the radius that you see here. And here the image is color-coded. The intensity scale tells you the number of stars per unit area. And then the color of it is telling you the metallicity of stars. And so orangish hues are of order kind of third to a fifth solar, and then going down to a little bit less than a 30th solar for the kind of bluer hues that you see here. And so you can see in the Andromeda galaxy, you have a very richly substructured halo on a variety of scales. And you also have a great diversity in the metallicity of stars in the halo, right? From very metal rich down to very metal poor stars. And so we're going to then, and so I'd actually like to start with thinking about, this isn't my own data, but it is more beautiful than my data. And so let's think about this data set first. And so Richard D'Souza and I wanted to build some intuition to try and learn about the hierarchical growth that has affected the Andromeda galaxy throughout its history. And so just to kind of introduce what some of the most salient features of the Andromeda stellar halo and its satellites are, compared to the Milky Way's halo, it is a very different beast, to the point where there was a big debate early in thinking about the stellar halo about what we should call many of these features, because there wasn't a feature that looked like our stellar halo. Instead, it was, much more massive, much more metal rich. And so folks were like, well, maybe it's just a really big bulge. It's like, well, fine, if it's at 60 kiloparsecs, then bulges don't mean what we think it means either. And so this stellar halo is 20 times more massive than the Milky Way. So it's a couple times 10 to the 10 solar masses. Many of the stars are of order a quarter to a third solar, right? Which again is quite different from the stellar halo of the Milky Way. Another thing that I didn't tell you about the stellar halo of the Milky Way, but is known to most folks, is that most of the stars in our stellar halo are pretty old. So we think of order 10 billion years. Whereas if you look at the star formation history in the interstellar halo in the giant stream, then indeed many of the stars have intermediate ages going down to several billion years old. And it looks like there was an episode of star formation about 2 billion years ago that affected the stellar halo of M31. So this is something that's also very different from the Milky Way that we'd like to understand. On top of that, there's one of the weirdest galaxies in the universe that's a very close neighbor of M31. It's the M32 galaxy. It's the most compact galaxy in the local universe. It's 10 to the 9 solar masses, has a Milky Way mass black hole. But it's about solar metallicity, but it lies well off the galaxy metallicity mass relationship. It's also has a very prominent intermediate age population. This was one of the great puzzles of Scott Traeger's thesis, and before that, Sandy Faber's work, to the point where Antonella Montecchesi's PhD thesis was measuring its star formation history well to try and confirm these really strange line index measurements that they had, revealing that it formed stars up until about 2 billion years ago. And so this is something that we'd very much like to explain. I see a chat message. Let me have a quick look to see what it is. Have you still lost the audio?
Mine's okay, so.
Okay, well, I'm sorry, James.
Oh, he's back.
Okay, good. All right, so these are the features that we'd like to try and understand about the Andromeda galaxy halo, right? But one of the problems is, well, actually, how do we understand that? Like, we got two different halos, and right now they're just different. And that doesn't really equate wisdom. That's just kind of an observation. Hey, those two things are different. And so, it also turns out that I never learned how to speak stellar halo at graduate school. I actually didn't have any classes really at graduate school either, because it was Britain. But even if I did, I wouldn't have learned how at graduate school. So we had to try and figure out how to speak stellar halo. And for this, the hydrodynamical models have been really very helpful. And so what we do is we try and build intuition by using these hydrodynamical models that I was showing you earlier to figure out how to connect the observed properties of halo to inferences about its merger history, right? And so these models have this hierarchical dark matter framework that we're used to, add approximations for how baryons should act and galaxies should form that end up in not totally implausible galaxies coming out of the end of it. And then also, because they have such large volumes, they track the satellite galaxy formation too, and their subsequent tidal disruption into stellar halos. And so they're able to link the observed properties or the properties of a stellar halo to what actually happened in the hierarchical growth of that galaxy. So they offer that opportunity. And so Richard D'Souza and I have spent quite a while thinking about this using this type of model. And the main thing that we've realized is that the largest single satellite dominates the properties of the emergent halo. And so this is, I guess, if you think about how galaxies occupy dark matter halos, it kind of makes sense that this should be this way. The galaxy, the halo occupation is incredibly steep, where a dark matter halo 10 times less mass than the Milky Way has a pretty massive galaxy in it, something like the LMC or the SMC. If I go another factor of 10 fainter, it becomes, the galaxy inside becomes much, much fainter still. And some of those halos, theory predicts, may even be devoid of galaxies. And so the large number of really small dark matter halos contain very few stars. And so you end up with a stellar halo that's really dominated by one big guy. And so whatever the largest guy was ends up setting the properties of the emergent stellar halo. This is shown in this diagram here from our work in 2018. It's the mass of the largest progenitor against the overall mass of the stellar halo. And one can see that this almost runs along the one-to-one line. And especially for larger stellar halos, they're composed almost entirely of the debris from a single satellite that was disrupted. You could say, hey, is there an observable consequence of that? And there is, right? The galaxy metallicity mass relation should imprint on stellar halos too. And this is something that we observed in Harmsen et al. 2017, and is a kind of generic outcome of hydrodynamical models, actually of all halo formation models. This is the illustrious version of that, and then this is the Ariga version of that. And so this insight and this kind of method actually generalizes across hydrodynamical simulations. And so with this in hand, right, with this insight that stellar halos, especially larger ones, tend to be the debris from a single satellite, or dominated by the debris from a single satellite galaxy, we can now return to Andromeda. So if we do that, we can now select from illustrious galaxies that have the same stellar mass as Andromeda, the same dark matter mass as Andromeda, as best as we can tell. And then those are shown in these colored symbols, right? The blue and the orange. And then what we show in orange is the subset of those that have large stellar halos, that have a stellar halo mass as large as Andromeda's. And one can see that invariably those systems that have large stellar halos had a merger with something that was large, above 10 to the 10 solar masses, and usually considerably above that, and metal rich, so having a metallicity of order solar, and that those mergers had to be late. And that's relatively easy to understand. In a galaxy or in a halo as low mass as Andromeda's, it actually takes a while for something as large as this galaxy to form that many stars and then merge in. And so these mergers would tend to happen in the latter half of the universe's evolution. And so there's an expectation that from the stellar halo, right? So there's a prediction that M31 should have merged with the galaxy about a third of the mass of the Milky Way, less than 5 billion years ago. And when we first came out with this, I was like, nah, there's no way, right? We should have known this, right? We know Andromeda so well. We really should have been able to infer this before. And so we thought, okay, well, what are the observational signatures? Let's check. Let's check what the observational signatures might be, so we can then compare with Andromeda, and if we want to rule this out. And so again, the hydro models are incredibly helpful in this regard. And so this is the progression of one of these interactions of a large satellite with Andromeda. The main body isn't shown. We just kind of show an ellipse that schematically shows the size of the interstellar halo of M31. And one can see that you have, actually the infall is several billion years in the past, about 6 billion years ago in this case, as its first apocenter 4 billion years ago, and then it ends up disrupting about 2 billion years ago into an extended stellar halo, which has a prominent tidal stream. So tidal streams are quite frequently reproduced in this kind of interaction. You do end up with an extended star formation history. And usually that star formation history stops when the galaxy is tidally disrupted. And that kind of makes sense, right? You have a whole bunch of gas in one space, it's forming stars and a satellite. And then when you tidally disrupt the core, that gas is also tidally disrupted and star formation stops. And you can also make predictions, relatively detailed predictions, as to what the predictions for example, metallicity and how that should vary across the face of the galaxy, when star formation shut down, even things like the rotation and dispersion signatures of a stellar halo formed in this way. And so without belaboring all the details, just returning to the kind of main headline observables, we realize that all of these features that seemed really unusual about M31 are signaling that that M31 experienced a merger with a large object several billion years ago. And so, we would infer that M31 merged with a galaxy about a third of the size of the Milky Way. We call it M32P for reasons we'll talk about in just a second, right? So we think, right, recall, actually I'm going back and forth, I'm sorry. Recall that M32, it has high metallicity, like the progenitor should have. It stopped forming stars a couple billion years ago, like the rest of the stellar halo. And so we believe that the core of this object still exists. It's been ground down essentially into M32 by the present day. This is why we call it M32P, progenitor of M32. So we think this is the core of this previous accretion. And actually, the black hole mass also kind of makes sense in that regard. It's got a Milky Way sized black hole. And it was roughly a Milky Way sized galaxy. The interstellar halo is where most of the debris is. And so you can be like, well, where's the rest of M32? It's like, well, it's all over the shop, right? Fills that entire image. And then the giant stellar stream, we think it's likely that that was caused by the accretion of M32P. Although we caution that when you have a big galaxy come in, it usually brings friends. And so there are a number of tidal streams that often happen at the time of a large accretion.
Eric, can I ask?
Yeah, go ahead.
Yeah, so in this scenario where something similar in size to the Milky Way merged with Andromeda,
yep.
And is it surprising that Andromeda itself wasn't more strongly affected?
I was surprised.
It's very thin, isn't it?
I was surprised. That it sounds like you're surprised too. Isn't that cool? Right? We learned something.
I mean, or alternatively, maybe the scenario.
So you're saying, well, this could all be crap. Now, the cool thing is that you can, right? You can go to the hydro models and you can ask, hey, can I ever get a halo like this without a large late merger? And the answer is no. Right? So that already kind of painted us into a corner where we're like, oh God, because I like you, I felt uncomfortable with this. I learned to live with my discomfort. The other thing that I think you'd be delighted by is that Francois Hammer actually independently ended up with this picture using the disk of M31 and its dynamical heating he had a whole suite of hydrosim. Because one of the things that's exciting about M31's disk is it's thick. So it's almost a kiloparsec in scale height. And it has a velocity dispersion. Actually, let me skip. I show the plot here. This is from Claire Dorman's work. And so the disk of the Andromeda Galaxy actually has a pretty high velocity dispersion of older AGB and RGB stars, corresponding to a few billion years ago. Francois Hammer thought, this is weird, and devised an entire project trying to figure out how to make that work. The only way he could do that is by having a merger event that happened a couple billion years ago with something that was a few times 10 to the 10 solar masses. And so just from his, and the two papers, they didn't know about each other. They were published about the same time. And so it's what I felt was like a confusing feature that, hey, M31 has a disk and it doesn't seem that screwed up. It is a little screwed up. It was affected by this merger, and that effect has actually been used to infer the same thing about Andromeda's growth history, which I thought was really quite cool. I do agree that you would like as much evidence as possible for building intuition about
Yeah.
Go ahead.
Eric, have you, excuse me. Yeah, just on that point, have you checked to see if this makes sense with M31's globular cluster system? Because M31's GCs are quite different than the Milky Way GCs, right? So here, basically the answer is yes and no. My problem is that I don't know how to speak globular cluster yet, right? And this sounds like it's, you know, a kind of flippant response. In the same way that I did not know how to interpret a stellar halo in a cosmological merger scenario, it's not entirely straightforward for me to understand what the signature should be of a globular cluster system. You know, M32P will have had its own globular cluster system, which you can imagine to be somewhat like the Milky Ways, right? And that it probably had metal poor globular clusters. It probably had some metal rich globular clusters. They may have been a range of ages of them. Andromeda proper had its own set of globular clusters, right? Probably also somewhat similar to the Milky Ways. I put those together. There's dynamical friction. The cores didn't merge, right? So you'd expect some angular momentum in, but not necessarily a super duper clear. It's not going to be like a rotating disk, right? The debris, oh boy, the debris is spread all over a relatively large stellar halo. And so there's going to, I think, be a relatively difficult correspondence of globular cluster properties to the merger properties, which is then complicated by the hydrodynamical models that we have access to not yet producing realistic looking globular clusters, right? And so I know there are efforts on this regard and lots of encouraging progress, but eMosaics, for example, just has the wrong globular cluster demographics to try and build intuition from. And so I feel like this globular cluster question is really important and is something that would be very, very powerful to understand and important to understand. I'm not convinced we have the theoretical tools necessary yet to be able to navigate that question well. Does that make sense as an answer? Yeah, I think so. But I think probably maybe I feel hopeful in like a few years the GCs and cosmological simulations might be there to actually do this test.
I agree. And I think that would be a wonderful and powerful test.
I don't think you need super fancy simulations though, right? To a good extent, you can just put in test particles and see where they get stripped off and how their spatial distribution and kinematics. You know, if your merger simulations are good enough and you get the right radial distribution with respect to the incoming thing, you should be able to show where they wind up in, you know, in 6-dimensional phase space. They're going to be roughly where the stellar halo is, stripped off a little bit more easily because they're more extended, right?
So they have quite different kinematics from the stars and the progenitors, right? The stars are in disks.
But you have
globular
particles.
clusters are not.
What I'm saying is you have particles that emulate those. So if you have simulations already, you can pick some dark matter particles and call them
And-
globular particles and just see where they wind
That,
up.
my friend, is the part that's tricky, is convincing yourself that you understand enough about which particles to choose. So I actually agree. Once you have those particles, so if you can convince yourself you know who to choose as a globular cluster test particle, then you're golden.
I think you just need you just need to choose a subset that mimic the mean, half system radius of the and we kind of know how that scales already.
I do not disagree that you could make some progress. The problem is it's a real project, right? So
Yeah.
I'm not trying to shirk it. It's just, this is a real project and we've been working on other stuff, but I agree it's important. And I think especially if any folks here want to actually sit down and think about it, I do think you're right that there is an opportunity using existing simulations and trying to pick a subset of either stellar or dark matter particles as proxies for globular clusters, that you could generate a range of possibilities which you could try and build intuition from. I'd be super interested in working with folks on that.
Just to point out a connection, this is actually a connection to your previous work, Mike. If you look at them in the phase space diagram, I mean, things come in on some orbit and they basically, wind up with some energy, and then the interaction that puffs it up a little bit so they can get a little more energy. So I think one thing is just the same way, if you measure age or metallicity, it's a kind of one parameter expression of something complicated. I think if you measured in effect orbital energy, that the first question is, how are the globulars distributed in the best estimate you can make of their orbital energy? And if you have a big blob of stuff come in a while ago, it'll be at lower orbital energy. So you'll see a bump, right? But the other thing I was wondering about was, can you measure the horizontal branch morphology at that distance? Because I thought in the Milky Way that you can, Alexa can correct me on this, but I thought you could separate out the accreted ones because the in situ ones have a tight horizontal branch morphology. I forget what that correlates with, but anyway, there's a tight sequence there, whereas the accreted ones are off that sequence.
Are you talking about the globular clusters specifically?
The globular clusters. I thought the Milky Way globular clusters, if you plot horizontal branch morphology against something, and I can't remember what the other thing is, metallicity or something, that you get a quite tight sequence. And then the ones that are outliers are the ones that were all accreted with satellites, right? But I don't, maybe it's too far away to do that. I don't know.
Not until JW. Sorry, Eric, for jumping in.
I was going to say, I don't know. Please answer.
Yeah, you're not going to be able to get down to the horizontal branch until JWST is up.
Okay, and you can't measure it from like UV colors or stuff like that? Maybe not, I don't know.
You may, but I don't know how much fidelity in different morphologies you can get from UV colors in terms of different morphologies. That I don't know that.
Okay.
And let me caution also that the intuition that one builds in the Milky Way is pretty good at telling us about the globular clusters, for example, that would come from a relatively small satellite that's being accreted. But when you eat a Milky Way, I've taken all. So there's going to be a whole bunch of what look to be completely reasonable Milky Way-like metal-rich globular clusters,
right?
But were nonetheless accreted, and so there's going to be a real disconnect between the observable properties of a globular cluster in terms of age, metallicity, chemical abundance, things like that, and its accreted versus in situ origin. So this is I think it's going to be a really rich and interesting problem. It's just one I did not feel like tackling right now.
Could I just jump in with this is Bill Harris.
Bill.
Oh, good. I'll mute myself.
Yeah. Gretchen and I are both listening here. For the horizontal branch types, there are already HST-based color magnitude diagrams for, I don't know, about 3 dozen M31 globular clusters that go well below the horizontal branch. JWST will be needed to reach the main sequence. that's non-trivial. I think as far as big mergers are concerned, the problem that occurs to me is to try to understand why there's so many metal-rich clusters in M31. The metallicity distribution of the clusters is more continuous than it is in the Milky Way, and they're relatively quite a bit more metal-rich ones. And even a fragment that's 1/3 the size of the Milky Way would not give you those terribly easily. So are those, Eric, do you see those as the in situ kind of results that have been spread out through the halo a bit more because of the merger sequence?
I have not thought through it anywhere near as much as you just have. So, and again, this is one thing where if folks want to get together and actually collaborate on thinking about this, I'm totally game. I think it's something that's really worth thinking about. We put some thought into it just to convince ourselves that it was not trivial, and so it wasn't a project that we wanted to wrestle with as something that, you know, it's like, oh well, you know, we'll spend a week making plots and then we'll figure out the core of it. No, it's not that kind of problem. I think it'll take more effort than that. I do think one thing I do want to say is that the stellar mass is something like 1/3 of the Milky Way, you know, maybe 1/4, maybe 1/2. That does mean that the dark matter mass is likely to be something like, you know, 1/2 of the other mass. And so then the globular cluster, if the globular clusters scale with dark matter halo mass, which some folks on this Zoom call are famous for postulating, then that would suggest that of order 1/3 of Andromeda's globular clusters should be accreted with this large accretion. And the other 2/3 wouldn't be. They would have been M31's original ones. And so how we want to make that split is then TBD. And that's also, it's, I think, something that that many of you are aware of is that M31 also had a significant episode of star formation about 2 billion years ago that was disk wide. And so I'm also curious the extent to which long-lived cluster formation might have been part of that. I don't think that we see evidence that there were lots and lots of globular clusters being formed in the actual final coalescence. And I'd be kind of curious to also learn about that.
Should probably let Eric finish up with the presentation so we can.
Yes. Well, this has been actually a terrific thing. Now, I do point out that it's now 12:20. And so what I'm going to do actually is I'm going to identify the 1 or 2. Yeah, let me show you one other thing, and then I'll finish up. So I wanted to also, because, you know, this group, it's actually been really fruitful to think about globular clusters and their interaction with a large merger event. Richard D'Souza and I, in part, we neglected the globular clusters because we started thinking about satellites, right? And so here is an illustration from Ekta Patel's work, where she's trying to illustrate the Magellanic, or the satellites that she thinks might have come in with the Magellanic clouds as they have come in and started merging with the Milky Way system. And so we've been trying to understand, again, using, in this case, actually dark matter only simulations, what happens to the satellites, at least relatively early in the infall and the infall stage before pericenter, when these galaxy groups merge. And so the kind of main message of that work is that you should actually have quite a lot of satellites that are accreted along with substantial merger events. And so this is shown here by, by referencing a single one of the Elvis simulations. We've looked at all of the Elvis or all of the Milky Way mass halos in Elvis. We just show one here to illustrate the main point, that you end up accreting quite a lot of satellite, potentially satellite-bearing subhalos at the time of a large accretion. And so this is infall time versus the number of infalling halos, and then those that survive to the present day. And so there's a big accretion at about 6 and a bit billion years ago, which brings in a whole bunch of satellites, many of which survive. And then the colored versus just the outline is those that are formally subhalos at the time at which is accreted, and those that actually, there's a substantial number that are not formally subhalos, but come in at the same time in a kind of correlated infall. They're a larger radius within the group that falls in. And so this, in Elvis, you end up with something like 15 to 60% of the satellites coming in with large accretion events. And it really, what it does, it doesn't necessarily change the number of satellites much, but it does cluster them in time of accretion. And so what we decided to do was to look at when star formation shut off in local group dwarf satellites as a proxy for when they fell into to their main halo. So for Milky Way satellites, you'd look at the star formation shutoff time as a proxy for, hey, when was star formation shut off by ram pressure stripping? The same deal for Andromeda. Here we show the histograms of shutoff times as inferred by Dan Wise and his collaborators for satellites of the Milky Way in blue, Andromeda's in red. The solid is just the distribution from the central values, and then the lines are kind of bootstrap draws essentially, or Monte Carlo draws from the error distributions. And so what one sees is that there's evidence of clumping in the star formation shutoff times of nearby dwarves, and they're clumped around 10 billion years ago and 2 billion years ago for the Milky Way, which corresponds to the time where we think the largest previous merger to happen to the Milky Way, the Gaia Enceladus merger, was about 10 million years ago. And then the LMC group fell in relatively recently and crossed the virial radius of order 2 billion years ago. In Andromeda's case, we see a clear signature about 6 billion years ago. This is one of the big differences between Andromeda's and the Milky Way's satellite star formation histories. And we note that this is the same time as the M32P group should have come across the virial radius. And so we think that there's actually pretty interesting and intriguing evidence of the infall of a large group 6 billion years ago, whose central galaxy merged with Andromeda 2 billion years ago, but many of whose satellites still remained, and we've measured the star formation histories of. So I think that's kind of a really neat, another potential angle that we can use to try and understand the hierarchical growth and the assembly of galaxies and nearby groups. So there were a lot of awesome questions, and I want to leave time for more of them. So I'm going to actually skip right to the conclusion slide. Point out that, so some of these we've had a chance to talk about. Other of the conclusions I will tell you in words, and then feel free to ask me about them either in questions or just in a separate conversation. So in general, we've learned that the stellar halo is a very powerful probe of the hierarchical growth of the galaxy, specifically the largest single accretion event. And we spent the whole talk more or less digging into what this implies for the Andromeda galaxy, realizing that something, at least to me, that was very unfamiliar and surprising happened to it, that there was a pretty large merger event 2 billion years ago that triggered disk-wide star formation, thickened the disk and heated it, and delivered a bunch of satellites. In other conversations, we can talk about, if you wish, work that our group is doing to try and tease out the anatomy of massive group accretions in other nearby galaxy groups. So again, to take the Milky Way and Andromeda and to generalize to a wider range of systems. This is this plot that we have up here, which is leading some interesting to some kind of interesting findings with respect to the number and the star formation histories of satellites as a function of the largest merger that a group ever experienced. So I'll just leave that there. I want to thank you for your time and for the excellent questions during this talk. And again, I should put my email in chat, but if anyone wants to chat with me separately about this, shoot me an email and we'll set up a time to talk. That's one of the funnest things about giving a colloquium in some places. And I know that we're impoverished of that right now. But thank you for your time.
Thanks very much. Live applause to go with the virtual applause. Very interesting stuff, really, really cool things. Yeah, we do have a little bit of time for a couple more quick questions if there are some.
I have one quick one. M31 stands out as being unusually compact, right? And that kind of system has, sorry, M32, that kind of system has been identified in other places, was my understanding. I mean, what are the odds, do you think, of turning that into a kind of observational test? Do you think we could go looking for nuggets like that and use them?
Yeah. So I agree. M32 is unusually dense and compact. Folks have looked at systems like that in nearby galaxy groups, and often go fishing for really big central black holes in them, right? Because if they're the center of big galaxies, the prediction is they'd have a pretty large black hole. And so, for example, Anil Seth and his collaborators looked at UCDs and are trying to find globular clusters around these ultra compact dwarfs in nearby groups.
There's
do also
one in Perseus, right? I think that's near 1275, and it has an extraordinarily massive black hole for its mass, but it's also close to 1275, I think.
Yeah, and I think that my recollection is there's a couple in Virgo also. One thing I also want to point out is that you can look for galaxies that are like M32 or these other galaxies, but before the merger. So you can find things that are a couple times 10 to the 10, but with a really compact core, right? And just say, hey, are there those lying around? Because this could have been a real problem with the merger scenario. It turns out that they do lie around, and 2 of them are in nearby galaxy groups. And so, let me just show. And so M51b, or NDC 5195, is one of them. It's got a really compact core, but then it's a couple times 10 to the 10. And M82 is another one, actually. And both of these are there are 8 in the local volume, of which 2 of them, so a quarter of them, are in various stages of merging with the central, which is kind of neat. And I think what could be really neat is to be able to study these types of local systems to build up an empirical picture of, well, what happens to the satellite, to the central, to the satellites that are brought in along with it, to the globular clusters as the merger sequence progresses, right? So in the same way we had the tumor sequence, right? I think we have an opportunity to build up a kind of D'Souza sequence of essentially minor mergers to help us understand the progression of a minor merger, which is kind of fun to think about.
The debate about the one in Perseus that I'm thinking of, which is closer to a giant elliptical, it's still compact if I recall, was whether it was a tidally stripped object or whether it was something like a red nugget, which kind of growth got stunted in some way, like it fell into the cluster. And I guess that's always an issue, right? We don't necessarily, unless we can see a stream that we can identify with the object. If you just see the remnant, it's harder to figure out whether it is a failed galaxy or whether it's a stripped galaxy.
Yep, and so this was something that we publish this in Nature Astronomy, and so you end up with like 1 million referees, and one of them was really kind of upset that M32 doesn't have a big tidal stream, and it's like,
wasn't me.
No, I don't mind. I mean, it's a legitimate thing, right? But the problem is that the stars around it in the center of the galaxy like that have 100, 200 kilometers a second velocity dispersion. And so they're going to be spread to the four winds in a way that's that's not going to look like a stream. Streams come from dynamically
Right.
thin, cold systems, so it can come
They're already hot, is what you're saying, because they're the core of a reasonably large size
And
elliptical.
so then it just goes, and you don't see squat. And so I do think that that observational test is going to be difficult. Instead, we suggest that the properties of the central galaxy, so for example, the age, the metallicity, the star formation history of the central part is an important discriminant in that regard. And in this case, it looks a lot like the middle of a Milky Way mass galaxy, right? Solar metallicity was forming stars more or less continuously, has a Milky Way mass black hole, and so it broadly fits in with that scheme. But I think that this conversation highlights what's going to be, I think, a foundational challenge of trying to infer the origin of a compact stellar system, that we're always going to be left uneasy. I think that's somewhat unavoidable.
All right. Well, thank you very much again, Eric. We are at the end. I really appreciate you making the time, and thanks to everybody for coming out. Again, please feel free to take him up on his offer and contact him by email if you'd like further conversation.
Absolutely. And just thank you for taking time out your day to chat like this. I appreciate it.
Okay. Have a great rest of your week.
Okay.
Bye.
You too.